Today I'm going to depart from the learning of the art of electronics for a project. I have the essentials laid out here. Books, not that book, but these two, active filter cookbooks, a board, a breadboard that is, and of course the most essential item of all, the cup of coffee. So what I'm going to be doing is working with a device that was invented some time ago. It's actually relatively obsolete. It's called a universal active filter. It's still made by TI. This particular one is called a UAF42. And for reasons that we'll talk about later, it's as I say, it's pretty much obsolete. It goes back quite a ways. This is actually a Burr Brown spec sheet for the UAF42. Burr Brown used to be the name in precision operational amplifiers. So their line has been acquired by TI. I don't know all the corporate details, but basically most of the devices that Burr Brown designed that are still of some use have now been taken over by TI. But the specific project that I'm going to work on is a project that I found on the internet for what's called a BiQuad bandpass filter. I won't talk about BiQuad too much, but I mention it because if you want to find information on this kind of an active filter, that's the name you should search under, is BiQuad. This is how it's spelled, B-I-Q-U-A-D. And in this, the reason I chose this, of course, is because it says to do this using a BiQuad, and then the particular filter that he uses is the UAF42. So here are the specs. I won't go into the details right now. Here is the circuit using a UAF42, and I have written in the pin numbers for the DIP package, and that's one reason that I like to try this one, is it's available in a DIP package, which is easy to mount on a breadboard. And this is the basic response we'll be looking for. So the next thing is to put the circuit together, that is the circuit here, and do some testing. And once again, we'll try to use the analog discovery to measure its frequency response and see whether we get something that approximates what the author expects. Before we embark on this active filter using the universal active filter, I thought it might be a good idea for those of you who have not studied filters in general, or it's been a while and you'd like a little refresher. There are fundamentally filters that pass a set of frequencies and filters that reject a set of frequencies. So, for example, there's a low pass, which simply means this is the ideal, this is what you actually get in practice, this is what's called ripple in the pass band, and this is called the band stop or the band reject. Similarly, there are high pass filters that pass the high frequencies. Once again, this is the ideal response, but this is what you really get. What we're going to be doing is a band pass filter, which is something that is designed to block frequencies below and above a certain range. And actually, we're going to be doing a narrow band pass filter. You can also have band reject filters. Now, one of the important issues with filters is the Q and its effect on the band pass. This shows how Q affects the bandpass for a one-pole. We're going to be actually using a pole pair, in other words, a two-pole BiQuad filter. And here you see the Q is 1 and goes up to about 20. The filter we're going to be building allows us to go up to almost 100 on the Q, which makes it a very, very narrow bandpass. Previously, I've talked about the fact that a low-pass filter, at least a first-order low-pass filter, is basically an integrator. And we studied integrators a couple of videos ago. In fact, the one we studied is what's called a lossy integrator, that is one with the resistor across the capacitor. And you may remember that I had some trouble because the basically, even though I went to a very large resistor here, I was not getting the error offsets that the author of the Art of Electronics lab manual was getting in his circuit, or at least was expecting us to get in our circuit. This, of course, is the ideal. You never have that. You always have some leakage from the output back to the input. The high-pass filter is often thought of as a differentiator, and the reason for a lot of these terms is, as I pointed out earlier, most of these circuits were originally developed before and during World War II for analog computers, and in that case they were using the mathematical terms differentiator. Today we tend to use electrical engineering terms, and we talk about high pass and low pass. But a high-pass filter is basically a differentiator. Once again, there's an ideal and there's a lossy. And of course, this resistor represents the loss in the capacitor. At some point, I would like to talk about switched capacitor filters. I won't in this video. But these are an alternative to what I'm going to be showing you later, which is the universal active filter. It is pretty much obsolete. There are lots better ways to do things. So here is an example of a simple bandpass filter. And basically, if you'll notice, it looks like a differentiator and an integrator. In other words, a high pass and a low pass filter together. And of course, if the low pass frequency is lower than the high pass frequency, then you have a band pass filter. If those are reversed, then you have a band reject filter. Here is a Filter Pro design report. I won't go into the details on this. This is basically what I did was I put into the TI design program a little bit of the values that we're going to be using, and just to see, because the Filter Pro program is the latest incarnation of the program originally developed by Burr Brown to design filters around that UAF42. Finally, I do want to summarize filter types, and you'll often see these. A Butterworth filter has the advantages that, you remember I mentioned the ripple in the passband? Well, the Butterworth has the least of the more or less standard filter types, has the least. It's generally okay in terms of its all-around performance, and it certainly is better for pulses than the Chebyshev, which we'll look at in a second. But the disadvantages is there is some overshoot and ringing in the step response. A Chebyshev offers a lot of advantages, but including a better skirt rate of attenuation beyond the passband than the Butterworth. But the ripple in the passband and the ringing cause this not to be a very good instrumentation circuit. It's good for stuff where you're listening to it, but it's not very good where you're measuring. Of course, there's an inverse Chebyshev, which basically has a flatter magnitude response, but it once again has ripple in the passband and ringing in the step response. The third, more or less general filter is the Bessel. And in general, the Bessel is the best filter if you're trying to measure something. It has certainly the best step response. There's very little overshoot or ringing, but it does have problems with the skirts, and you often have to use a higher order filter, in other words, more op amps, to with a Bessel design to get the same skirt steepness that you can get much more easily with a Chebyshev or a Butterworth. What we're going to be doing is actually a pole pair BiQuad filter. So let me show you a little of what that looks like. And for those of you who appreciate nostalgic war stories, of course no one appreciates them more than the person telling them, but this is a book that I bought in 1972. I was finishing my bachelor's degree in electrical engineering, and it's a book that was published by Burr Brown. But one of the reasons that I bring that out isn't just to recall old times and old friends, but this is the circuit that we're going to be building. Here he calls it a second degree state variable network, but it is essentially a BiQuad filter. And this design, or similar designs, are what led Burr Brown to eventually produce the device we're going to be using, called a universal active filter. At any rate, I don't know if these sort of nostalgic returns to the past do any good, but they certainly do call up a lot of old memories. Here is a BiQuad filter, and this is actually out of AB035, which is the Burr Brown application bulletin. You can find that on the internet if you look around for AB-035. It uses three operational amplifiers. It has characteristics that can be adjusted by resistors, and one of the big advantages of the BiQuad is that the frequency response, in other words the bandwidth, does not vary much with a change in center frequency. And for that reason, it was used in a lot of early spectrum analyzers where you have a resolution bandwidth and you want it to remain relatively constant, and then you want to sweep the filter over a range of frequencies. The center frequency is adjusted by the value of the feedback resistor. So if, for example, you put a potentiometer in here or a variable resistor, you can do it that way, or if you want to do it electronically, you can put a device with controllable resistance here, like a MOSFET, and control the frequency that way. The Q, remember, that determines the actual bandwidth of the circuit, is set with this resistor RQ, and the gain, the overall gain of the stage, is set by the value of this resistor. So basically, by changing these three resistors, you can change the frequency, you can change the bandwidth, and you can change the gain. So that is the filter we're going to be building. And now we've connected the analog discovery, in this case the analog discovery 2, running the network analyzer. We are running from, in this case on the left, 100 hertz, and on the right 20 kilohertz. And you may recall we're looking for a 1.2 kilohertz bandpass filter with a Q of 10, as I pointed out earlier, the nice thing about this particular circuit is you can run the Q way up. You can run the Q up to 100 by varying that Q resistor that I showed you earlier. But this is the peak. It's 40 dB, which of course is a gain of 100. And this is the phase response. And as you see, there's a substantial change in the phase from negative to looks like about 80 to negative 240. We can change that a little bit by, let's do the, well, no, let's not bother with that for now, because what we're mainly interested in is the filter response and the 3 dB frequencies. So let's zero in on that, and instead of starting at 100 hertz, we're going to start at 500 hertz, and we're only going to go up to, let's say, 5 kilohertz. And it looks like we're going to have to allow for a little more gain there so that we can see that. Well, let's go, instead of to 5 kilohertz, let's go to 2 kilohertz. And maybe at the low end we'll go to 1 kilohertz. There we are. Now, so this is the 3 dB points will be from about here, which is it looks like it's got about a 200 hertz bandwidth. Which is well within the specifications. If I remember right, let me take one last look at the specs. Well, it says a bandwidth of 120 hertz. So that would be from about 1.08. This is 1 kilohertz here. So from about there, that, yeah, it looks like that's pretty close to 120 hertz. Now, let me show you the schematic and a couple of the small compromises that I had to make in this circuit, and then we'll finish up this video. So here is the circuit once again, and the original design called for 132K here and 100K there. That's very close to 100K. I'm actually using 131K instead of 132K resistors there, and the reason is that what I did is I selected a couple of 150K resistors, and then I padded them with some 1 meg selected resistors. And by selected, what I mean is I chose values. These are 5% resistors, so I chose values that were 5% high or 5% low, depending, or near the edges, in other words, to get as close to 132K here and 132K here as I could. Also, my feedback resistor, which, as you may remember, the feedback resistor adjusts the center frequency. Well, I'm actually using a 47K here, which measures close to 48K. So, once again, the only purpose in this, partly nostalgic and partly informative, was to show how this universal active filter could be used to construct a bandpass filter. Now, it can create a low pass, a high pass, a band. It's a universal circuit. But because it's a little bit out of date, I'm not going to go into much more. But I do hope that what you have seen here is at least informative, and understand that you can do the same thing yourself without having to buy this UAF42, which is a little expensive. It costs about $20 in single units. But let me show you the breadboard. Right here. And the UAF42 is right there. I don't think you can see, but it actually is a burr brown. If I get a little bit closer. Nope, it's not going to focus. Okay, well, anyway, take my word for it, it's a burr brown chip. The TI makes them today, but I just happen to have an old burr brown UAF42, so I thought I'd try this. At any rate, as I say many times before, I hope this has been at least somewhat informative and maybe a little entertaining. But whatever you get out of it, let me know. I do appreciate comments. I generally don't respond to comments unless the person asks a question that might be of general relevance or brings up a point that raises an area that perhaps I haven't talked about or whatever. But I do read all the comments, so please let me know. And in the meantime, I hope you have a nice day.